Now we build the same stack with a linked list. Each item is a node on the heap. One pointer called top names the node on top. Let's push a new node and then pop one off. To push, we make a new node, write its value, splice it in front of the stack, then move top. The old stack, top to 30 to 20, stays on screen the whole time. Nothing shifts and there is no fixed capacity. Watch the new node in green. Step 1. Allocate. We call malloc and get a fresh, raw node at address 4000. Its data and next fields are garbage for now, shown as question marks. The stack below it is untouched. Step 2. Write the data. We set X arrow data becomes 40. The new node now holds its value. It is still not linked to the stack, so its next is still garbage. Step 3. Splice. We set X arrow next becomes top. So node 40's next field now holds 2000, the address of the old top. Watch carefully. Top itself has not moved yet. It still points at node 30. Step 4. Move top. We set top becomes X top now holds 4000, so it names the new node. The push is done. It is big O of 1 because nothing shifted and nothing was copied. Now the push in C, the function is called lspush. It takes top by address, that is a pointer to the top pointer, plus a value v. It returns 1 on success, or 0 on failure. That way, a failed malloc is never confused with a real stack. First, we call malloc to ask for one S node of memory. We keep the address in a new pointer called x. Next, we check the result. If x is equal to null, malloc failed. We return 0 and leave the stack unchanged. Now we fill the node. We set X arrow data becomes V, so the new node stores the value. This is the splice. We set X arrow next becomes star top. The new node now points at the old top. Then we move the top itself. We set star top becomes X because we took top by address. This updates the caller's own top pointer right here. Last, we return 1 to report success. The whole push is big O of 1. 1 malloc and 2 pointer writes. There is no walk, unlike inserting at the end of a list in Chapter 4. To pop, we check the stack is not empty, read the top value, save the node beneath, move top down, then free the old node. The order matters, so watch it one step at a time. The stack stays drawn the whole way. Step 0. The guard. Before we touch anything, we check is the stack empty. The stack is empty when top is null. Here top holds 4000, so it is not null. The stack is not empty and the value 40 is on top, ready to remove. Only after this check do we go on. Step 1. Read the value. We set out becomes top arrow data, so we save the value 40 into out. The structure of the stack does not change yet. Step 2. Save below. We set below becomes top arrow next, which is 2000. We remember the node beneath before we free anything. Step 3. Move top. We set top becomes below, so top now holds 2000 and it names node 30. The old node is now detached from the stack, but it is not freed yet. Step 4. Free. We call free on the old node. Because it is already detached, freeing it is safe. It is grayed out to show it is gone. The pop is done and it is big O of 1. Now the pop in C, the function is lspop. It takes top by address. That is a pointer to the top pointer and a pointer called out, where it will place the value it removes. It returns 1 on success, or 0 on failure. First, the guard. If star top is equal to null, the stack is empty. There is nothing to pop, so we return 0 right away. Next, we remember the node we are about to remove. We set old becomes star top, so old points at the current top node. Now we read the value. We set star out becomes old arrow data. This copies the top value out to the caller. Then we move the top. We set star top becomes old arrow next, so top now names the node below. Because we took top by address, this updates the caller's own top pointer. Now we free the old node. It is already detached, so freeing it is safe. We never read a node that we already freed. Last we return 1 to report success. Pop is big O of 1. 1 read, 1 move, and 1 free. There is never a walk. The same empty test, star top is equal to null, guards it. Now a quick check. Both stack pushes are big O of 1 but for different reasons. Why is the link stack push big O of 1 with no walk, unlike inserting at the end in chapter 4? Pause and think. Now the answer. Top always names the head node directly. So a new node splices in at a known address, and we never walk to find the tail. Insert at the end has to walk, unless it caches a tail pointer.